We need to start talking about different models of molecules. And one of the models we're going to use is the Lewis model. The Lewis model is a great way for us to represent molecules in two-dimensional space. Okay, so it's not showing the actual bondings or anything like that. It's just a 2D representation of the molecules. We do have a set of rules we're going to follow to write out the Lewis structures. So you can see the rules here. Steps for drawing Lewis structures. First thing we need to do is sum up all of our valence electrons from all of the atoms in the species or in the molecule we're looking at, and we need to take into account any positive or negative charge on those species. Positive charges mean I have one less electron than predicted. Negative charges mean I have one more electron than predicted. You need to determine which atoms are connected and how they're connected. And part of this just comes from practice, okay? There's not an intuition from practice. But usually the central atom is listed first. That's not always the case, but often the central atom is listed first. In some cases, the formula actually describes how they're connected for you. In oxyacids, the hydrogen atoms are bonded to the oxygens, which are bonded to the central atoms. You're going to have to recognize oxyacids, but we will talk about them when we see them in examples. And also, the least electronegative element is usually your central atom. So we go by electronegativity. The more electronegative it is, the more likely it is to be an outer atom. The less electronegative it is, the more likely it is to be a central atom. You're going to distribute all of the valence electrons in this order. First thing you do is connect the atoms. Every single line connecting two atoms represents two electrons out of those valence electrons we added up. You're going to complete the octets on all of your outer atoms. There are some exceptions to this, and we're going to see that. You're going to put any leftover electrons onto your central atom. You're going to check to see if the central atom has an octet, and if not, you're going to use multiple bonds to accomplish this. Again, there are exceptions, and we're going to see some of those very intentionally in the first few examples we do. You're going to assign and minimize formal charge. We will talk about formal charge in another module. And then you're going to draw resonance structures as needed. Again, we will talk about that as well. So let's do some examples here. PCl3, SO2, and CF4. If I look at PCl3, when I look at the periodic table, I see that phosphorus has 5 valence electrons. So I've got phosphorus and 5 valence electrons. I see I have 3 chlorines here, and every chlorine has 7 valence electrons. Again, it's the old group numbers or the current group number minus 10 if we're in the P block to get to your number of valence electrons. So group 13 has 3, group 14 has 4, group 15 has 5, 16 has 6, 17 has 7, and 18 has 8. If you're in the metals, don't subtract 10. Okay, add this up. 3 times 7 is 21, plus 5 is 26. So 26 valence electrons. The first atom listed is my central atom. In this case, it's also the most electropositive or the least electronegative, which is also how I know it's a center atom. I've got phosphorus, and I'm going to connect all of my other atoms to that central atom. So phosphorus connecting the chlorines to it. I'm going to give my outer atoms their octet. Each chlorine had 2 electrons to start, 2 from the bond to that phosphorus, that single line of the phosphorus. So I give them each an additional 6 electrons to give them each their octet. So now each chlorine has its octet, and if I add up all the electrons right now, I would have used up 24 electrons. 2, 4, and 6 from the lines themselves, and then the additional dots add up to 24. Add the extra electrons, any leftover electrons, to that central atom. We check and see, does that central atom have its octet? And it does. It has 6 electrons stuck in the lines themselves. So again, 2, 4, and 6. And then it has its 2 electrons here, and its one lone pair has 2 electrons, 8. So our central atom does have its octet. Now, we haven't learned formal charge yet, but I can tell you this is the correct structure. Okay? Let's go ahead and work on SO2. Sulfur, 6 valence electrons, 2 oxygens, 6 valence electrons each. 6 times 2 is 12, plus 6 is 18. I have 18 valence electrons in SO2. Sulfur is the least electronegative, so I'm going to put it in the center, and I'm going to give oxygen the outer atoms here. I've connected each oxygen with a single line. Again, that single line represents 2 electrons for each line. So that's used up 4 electrons. I'm going to give those outer atoms their octet. If I add up all my electrons so far, again, each dot counting as 1, each line counting as 2, I've used up 16 electrons. I have 18 total, so I'm going to give the last 2 electrons to that central atom. Now, the last thing I need to do is check to make sure that central atom has its octet, and it does not have an octet yet. So what happens is one of these oxygen atoms will donate one of its pair of electrons to form a double bond to that central atom. Now, both the oxygen still has its octet because those electrons are being shared. So again, this here represents 4 electrons, and the oxygen itself has 4 electrons in its 2 double bonds. But the sulfur has the 4 electrons there, 2 electrons here, and 2 electrons here. Overall, 8 electrons to sulfur. So that does have its octet now. Now, some students may say, why did I give the double bond from that oxygen and not the other one? Well, that's where resonance comes into play. And we're going to talk about this again in another module, in another part of this chapter. But this could also be written with the double bond over here. These are technically different atoms because this is like oxygen 1 versus oxygen 2, oxygen 1 versus oxygen 2. And so the double bond could have gone between the sulfur and the oxygen 1 or the sulfur and the oxygen 2. That is a resonance structure. These two happen to be equivalent. They're not always equivalent. And we will see what I mean by that as well in the practice. How about CF4? C is carbon. Carbon has 4 valence electrons. I have 4 fluorines. 4 times 7 valence electrons. 4 times 7 is 28, plus 4 is 32. Carbon is the least electronegative of these two species. Fluorine is the most electronegative element there is. So I'm going to connect my fluorines and give my outer atoms their octet. Now, if I counted up all my electrons, I've used up all 32 electrons. Each fluorine is accounting for 8, and there's 4 of them, so 8 times 4, 32. I've used up them all. I don't have any to put to my central atom. I check my central atom. My central atom has its octet. It has 4 bonds to it. Each bond represents 2 electrons. My central atom also has its octet, so therefore I'm good to go. We'll learn how to check formal charge in a future module again, but again, this is the structure for CF4. Okay, what about these ones? H2SO3, XeF4, and PCl5. These 3 are intentionally listed because they are not going to follow your nice Lewis rules. Let's see what I mean. I have 2 hydrogens, 2 times 1 valence electron each, 1 sulfur, 6 valence electrons, and 4 oxygen, 4 times 6 valence electrons each. Overall, this gives me 32 valence electrons. Now, what you have to recognize is that this is an oxyacid. How do I know that? Well, I know it's an acid because I've got the H2 in front. That gives me, 2H pluses and an SO4 2 minus. So I know it's an acid. It's an oxyacid because I have oxygen in the species. So if I had just a binary acid, that'd be like H2S. That's a binary acid, okay? Oxyacids, you're gonna have oxygen in the formula. It's gonna come from a polyatomic. So like your sulfates, your phosphates, phosphite, nitrate, nitrites, arsenates, carbonate, all of that. They all have oxygens in there, all coming from a polyatomic as well. In this case, your hydrogens are attached to oxygen atoms. So it's easiest to kind of think about it like sulfate first, and then your hydrogens connect to an oxygen atom. Do they have to be the 2 outer oxygens on the sides? No, it could be the top and bottom. I just drew that way for space. Give all of your oxygens their octet. Hydrogens can only have 2 electrons, so the hydrogens don't go past the single bond there. They can't have any more. They literally only have space for 2 electrons. Right now, I've used up all 32 electrons. technically speaking, my sulfur has its octet, but when we do the formal charge here, which again we will learn coming up soon, we do formal charge, we're going to find out that this is not actually correct. It's going to form a double bond here and here. Okay, so again, you're gonna have to trust me right now, but this is gonna be the actual structure of sulfuric acid. If I look at XeF4, Xe is a noble gas. Noble gases have 8 valence electrons. People are gonna say, but it's a noble gas. Why is it reacting? Truthfully, xenon's just big enough it can. It doesn't, it's the outer electrons that are bonding, and xenon doesn't care at that point. It's so large that it's gonna let those outer electrons bond with things and stabilize it. It's not gonna make a difference in the noble gas. Doesn't bond with a lot of things, but it will bond, and xenon will make molecules. Four fluorines, 4 times 7 valence electrons. 4 times 7 is 28, plus 8 is 36. So Xe, F, 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 and F. Give all of your outer atoms their octet. Now, if you count, I've only used up 32 electrons. The rest have to go to the central atom. You're going to give it to it in pairs, though. So 2 and 4. You're not going to draw them next to each other. It's always in a pair, a lone pair. It's a pair of electrons, so 2 electrons paired up. So I can draw them like that. You could draw them like this, like this. It doesn't matter as long as they're not next, as long as they're not in the exact same spot. I can't draw like that. Okay, they have to be opposite. They have to not be on the exact same side of the xenon. But that would be the correct Lewis structure for xenon. Now, it looks like xenon's got more than an octet, and it does. But again, this is the correct structure. It's just what we call an expanded octet. So we're going to see that come through as one of the exceptions we have to the rules. And PCl5. Phosphorus, again, has 5 valence electrons. I have 5 chlorines here. 5 times 7 valence electrons. 5 times 7 is 35, plus 5 is 40 valence electrons. My phosphorus and connect my chlorines. And give every chlorine its octet. Notice I've used up all 40 electrons, so I don't have any left. This is the correct structure. And I check, and phosphorus has more than an octet, but again, this is allowed. So let's talk about those exceptions. We just saw a couple of them. We saw 3 examples of exceptions. First off, we do have atoms that routinely have less than an octet. It doesn't mean they have to have less than an octet, but they like having less than an octet. Beryllium really likes to have 2 bonds. So kind of a quartet. Boron and aluminum really like to have 3 bonds. So a hextet. Molecules with an odd number of electrons. I avoid these in practice for you guys, okay? If I write one in, it's by accident. I won't do it on assessments. I've taken the one out of the practice in here. But you will see this when we get to things like organic chemistry. Molecules with an odd number of electrons literally cannot obey the octet rule. It's not possible. They are extremely reactive. They're called free radicals. They're extremely reactive because they have that unpaired electron. They want to not have it. They want to pair up with something. They want to keep reacting to counteract that effect. So they will have unpaired electrons. We will not deal with that in this class directly, unless we're talking about it in a specific situation, but you won't be drawing the Lewis structure of it. Third row elements and below can have more than an octet. We saw in the previous slide, we saw phosphorus, sulfur, xenon, all having more than octet. We call it an expanded octet. And you're going to see that they can have more than just their octet, just more than just their 8 electrons. And why does this happen? Well, third row elements and below have empty d orbitals in their valence shell. So remember your your s atoms are in the p block, but they're in the third energy, n equals 3 energy level of the p block. They have empty ds. They can put electrons in the d orbitals if they want to. So not only do they have empty Ds that the electrons can go into in their valence shell, but they're also the atoms themselves, the atomic size of it is large enough that it can accommodate more than four bonds. Below that, your N=2 energy level and above are so small they can't accommodate it. And the reason this is important is things like oxygen, nitrogen, fluorine cannot go past your octet. Sorry, it's really, really hard for me to write that low. They can't go past your octet. So we're going to see that come through as well. Those ones literally cannot do it while things below them can.